Welcome to another episode of XR Talk Show. Start Wolfram Language. Advent of Code. Day 2. The shortest solution on Earth. Let's begin. Let's start Wolfram Language and magnify the window. Let's say 3. Shift Enter to run it. Shift Enter 3. That's good. Now, Advent of Code, Day 2. So here is the shortest solution on Earth. Paste it. That's a code. Run it. What? Suppose what? Oh, you forgot to add the input. So start again, select all. So here is the input. It's magnify the lines, okay, and shift enter. The answer is 8. Fantastic, shortest solution on Earth. Now advent of 2, problem, day 2, problem 2. Copy. Paste, okay, so here's the input and here's a solution. Run it. 228686, fantastic, the shortest solution on Earth in Wolfram language. Hello, welcome to another day of XR Talk Show. How are you guys? So today's job is to explain these shortest solutions of Advent of Code, Day 2. Then I'm going to work on Day 3 live. I haven't coded yet. I read the question, but I haven't coded yet. Okay, so let's go over Day 2. Day 2, last week, I started to do it live and screwed up, end up 1 hour, didn't do nothing, but then I finished. So in the Advent of Code, everyday solution I'm gonna code in Wolfram language is gonna be the shortest possible. Okay, let's magnify the font. Can we magnify the font? Let's just do it this way. Okay, so Advent of Code. So what is the problem? Advent of Code Day 2. The first problem is that you got a bunch of lines like these. Can you see? Okay, so let me do something here. Can you see? Oh yeah, so you need to, yeah, okay, so what is the problem? Day 2, problem 1. So you got a bunch of lines like that. Let's go here. Okay, so you got a text input, a bunch of lines. And some are blue, some are red. For each line, you have a game number, then 3 blue, 4 red, and so on. So each line describes a game, and each semicolon field shows a draw of colored balls. Okay, so like that. And given info that there are a total of 12 red balls, 13 green, and 14 blue. In other words, we have some kind of hash table like that. So 12 red, 13 green, 14 blue. And for each game, so for each line, if any of the number is greater than the possible max, cross out that line. For the remaining games, sum up the game number. So the input is a bunch of lines. Each line has a bunch of blue, red number, 1 red, 2 green, 6 blue, 2 green. And if any of these colored number balls is greater than the given number for red, green, blue, you cross that line out. Then for the rest of lines, you add their game number. Okay, that is the solution. So the solution for Advent of Code Day 2 Part 1 is this. Okay, so let's copy it and let me show you how that works. Okay, so where do we do it? Okay, so let's do it here. Hello and say hi. Good night all. Hello, because I managed to get solution that day. modify your initial code. Fantastic. Yeah, I'm so late. I'm kind of, anyway, let's continue the explanation of day 2's code. Okay, so what is this? Talk show. So then after today, after I explain the solution for day 2, I'm going to start day 3. And I should, it's day 3, it's going to be one single line too, within, let's say, 200 characters, one single line of no more than 200 characters. In fact, like I said, every day's advent of code in Wolfram language is one single line. I would say no more than 300 characters, okay? So anyway, so here is the day 2, problem 1. So you got a bunch of lines and run this code. So let me explain this code, okay? So for example, I can run it now. Run it. 8, right? You see the problem solution is 8. Now, if I run with my own input, now you see this read string and this file path. Now, if we open that file path, you can see there are a total of 100 number lines, red, green, blue, and stuff. So we are going to do the input, my personal input. Run it. So the solution is 2512. So I obviously I passed. So that is the day 2 part 1. So now let's explain how this single line of code works. Okay. Now how many characters are there? The region has one line, one sentence, 25 words, and 170 characters. Fantastic. Okay. Now let's explain how this code works. Okay. Now let me just do something so that it's more readable. String cases. Okay. So okay. So let me just reformat the code and do something so it's in a most readable form. Okay. So let's put that. Okay, so let's do X max. Let's X max. So let's move this out. So this defines a dictionary. Okay, so green 12, green 13, red 12, blue 14. This is a dictionary. So here max, we move it. We just embedded that constant into our code. That's so that shortens, that shortens the variable name and that. Okay. So let me finish. I'm gonna explain the code how it works. So I need to add some spaces so that so that it all makes better sense. Now, okay, so put it here. Okay, so the algorithm is this. So for each line, you have this green, red, blue paired with a number. So you want to parse it so that if any one of these pair, number green, number red, a number and a color, is more than this given red, green table, then you remove that line or ignore that line. So what you do is first of all you do string cases. Okay, string cases return. For example, string cases. Yeah, you don't even wait. You have to split. Yeah. So first of all, you split the string into a list, right? So then you pass each list item. Each list item is one of these line. Okay, then for each line you use a string pattern to check the pattern. The pattern is to find the number and pair. So one green is a pattern, 3 red is a pattern. So you want to capture those patterns. Okay, so the way you do that is you use string cases. Okay, so oh god, when you start to explain it, it's gonna take half an hour. String cases. Okay, so string cases is take a string. Okay, obviously first of all takes a string. Let's say A B C D E F G, and takes a pattern. Let's say A. Okay, so takes a pattern A. So that will return all occurrences of this pattern. So in this case, it's just one thing. In fact, we don't need this list. Okay, so let's do it again. So it's one thing, A, right? So if you say regular expression, let's see. Oh my god, if I'm gonna explain this, it's actually gonna take half an hour. So regular expression dot stand for any character, right? So if you do that, you got all these bunch of characters. You got A is a match, B is a match, and the space, empty space is a match, C is a match. So let's try another example, okay? So let's say B something, D88, E99, okay, some number. Now we want to regular expression. We want to find all cases, string cases, all cases that start with a letter, then followed by a sequence of numbers. Okay, so in that case, so start with the letter, so that would be square bracket A to Z, okay, or backslash W, I think. Yeah, we can do that. Anyway, so A to Z, then followed by 0 to 9, or backslash D. Okay, so, and one or more. So plus means one or more. So if you run that, you see you got all the cases, occurrences, B283. So string cases, that extract substrings by a pattern. Okay. Now in Wolfram language, you have to specify a string pattern. There are two ways. One is the normal regular expression everyone is familiar with. Every programming language has it. Java, Python, Ruby, Golang, blah, 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 PHP, regular expression, ancient, old. Okay, but in Wolfram language, you have another syntax to specify a string pattern. Equal power with regular expression, but much more readable. Okay, that is called string expression. Okay, so let's do this the same thing with the string expression syntax. Okay, so let's do that. String expression. Okay, EXPR. So I'm kind of going. Okay, so what do you want to match? The first of all is a letter. Letter character. Okay, this symbol, you see, Wolfram language is a symbolic language, just like Lisp. Everything is a symbol. In this case, this letter character is a symbol, and it stands for basically A to Z, or capital letter, depending on if you ignore case or not, but basically A to Z. Okay, so you want that, begin with that, then you want to follow by digit. Okay, digit character. Okay, another symbol that stands for all digits. Okay, and you want it to occur more than once. Okay, so in that case, the syntax is underscore. Okay, that I think so. Let's try it. Okay, run it. There it is. Wait. Digit character. Wait, we got it wrong. This E99FG. Am I doing good? Am I can you guys see it? Check my status. Okay, say hi if you are watching. Okay, so and ask me questions if it's not clear. So we almost got it. So the letter character. Okay, some syntax. So you have to look up. Basically, you have to look up the string expression syntax here. So let's do. Okay, at this rate, I cannot start day 3 every time. It seems so simple to explain but once you actually start to explain it, it takes half an hour or even an hour. Oh, good, fantastic. Okay, so we are looking at the documentation for string expression, which is a alternative to regular expression, okay, which is in fact easier to read. So now we are, doing the same thing with regular expression and string expression, but except the string expression, we got something wrong. That's why we got different answers. So letter character, why does it repeat? So let's check the syntax. One or more characters. So and why is this digit character not so hold on a second. So let's magnify this. So you are looking at the string expression syntax. Digit character 0 to 9, and letter character is just a letter, right? And for this example, we want, so there's one single letter character, but why does it return AB to A3? One single letter character. So let's look again. String, any single character, a substitute of one or more characters in a substring of one or more. Okay, so pattern. So you have to okay, so I think what happened is that this, oh yeah, I know. So the letter character is not just one single character, it's actually more than one. So if we do it again, oh, now wait, now it's one single character. Okay, so, oh, okay, so digit character must be one or more. So, yeah, I got it wrong. So it should be dot dot, okay? Not underscore. Underscore stand for anything. So digit, so letter character is just single one. And digit character, we want one or more. So one or more is dot dot, okay? Let's do it. Fantastic. Now the answer is exactly the same as our regular expression, okay? Now let's remove our error. So there. So great thing, okay? String expression is a alternative syntax to regular expression, but kind of more readable and compatible with the Wolfram language, because the entire Wolfram language is a pattern matching system, symbolic pattern matching. You hear about pattern matching all the time from Haskell, from meta language, from OCaml, these functional languages. Their pattern matching is structural and type system pattern matching, Haskell, for example. But the Wolfram pattern matching is symbolic pattern matching. In other words, it's syntactical pattern matching. Okay, so it's different. So anyway, so string expression is alternative syntax to regular expression, and the syntax for string expression is compatible with Wolfram's symbolic pattern matching syntax. So anyway, so that's about that. So now let's go back. So when we call string cases, now there's more advanced use for string cases. What if you have multiple string? Okay, you usually in other languages you use a map. You create a lambda and map it to a bunch of strings. But in Wolfram language, you can put a string. You don't have to use a map. You can just put a list of strings here. So for example, I create a list of strings. So another item. So let's say x62, and do it. You see, you got x62. So let's try another TTH22. You see? So you don't even have to map. So that is why in our solution, we call string cases. Okay, we call string cases. String cases takes 2 arguments. So here's 1 argument, here's a second argument, 2 arguments. The first argument is the split string of the entire input. So each string is a line. So the second part is the heart of the solution, the second part, okay? Now we explained so far here we are using string expression to extract strings. Now you can actually do replacement. So for example, okay, so let me show an example. So whenever what happened? Undo. Okay, so whenever you see, let's say whenever you see a digit character, okay, you want to replace it by, let's say replace it by X, capital X, okay? So given 2 strings, this one and this one, whenever you see a digit character replaced by capital X, okay? Do it. See? Fantastic. Wait, why does it replace A and B? Something is not right. Let's try it again. Now let's try a simpler. Let's just say whenever you see T replaced by capital X. Okay, so I'm not sure what's going on exactly, actually. What's going on? What's going on with my keyboard? Oh. Okay, so whenever you see T replaced by X, and this is not what I expect. Oh yeah, right. So it, first of all, it finds the match. Then whenever there's a match, it does that. It's not a simple replacement. So when you do this, let's try again. So for example, when you do this, you see, when we do this one, it returns this, right? Now, of this result, then we can say, for example, let's copy that, okay? Let's remove it. Okay, so exact the same input. Now, out of this result, you replace it by X, for example. So you see, you got a 2 list. The first one is 3 items. The second one is 2 items, exactly. And because you say, whenever you found this pattern, you replace them by X, so that's why you get that. Now, the more interesting thing, it becomes interesting when you have a captured pattern. So you want to capture, let's say, whenever you see letter and digit, just remove the letter, okay? So for example, X62 will become 62. H22 will become just 22. Okay, so let's say we want to do that. So you give a name. So you give a name to the string expression. So the way you give a name, you can say X, you can say X colon, okay? So now this X is a name for whatever pattern that follows. You see? So in regular expression, normally you capture groups and the name is numbered. So you have the first capture 1, 2, 3, and so on. And you can also give a name. But in Wolfram string expression syntax, it's much simpler. You just start with X colon, okay, then whatever pattern. So So in this case, what we want, actually I haven't done this. To explain this, okay, so let me try to do this then. Okay. So let's look at the, yeah, okay, so I guess you have to do fixed order. Okay. So fixed order, letter, character, and digit, okay? So we have a pattern named X and actually that's not what we want. So let's move the letter character out. So string expression, the first pattern is letter character, okay? Then followed by a named pattern, and this named pattern is simply, yeah, okay, so I know what to do. The named pattern is simply digit character, dot dot, dot dot means one or more, okay? Now we are missing a bracket. No, wait. Yeah, we need a bracket. Yeah, so string expression start with the letter character, then the second pattern is a digit character, but we give a name X. Now we want to replace, whenever you found this pattern, string expression, you want to replace it by X. That is the digit character, okay? So let's do it. Run it. There it is, fantastic. Okay, so that explains another feature of the string cases function, which means once you captured some group, you can, some pattern, you can actually do replacement, okay? And this is what we are doing, okay? So so this is the, let me show you this pattern, okay? So let me show you, okay, so this code is very terse. So what we are trying to capture here is a number string followed by one of the red, green, blue. Okay, so that's what this is. So let me copy it, paste it here. You see, that's a pattern. But now let's do input form. Let's see. Okay, so actually let's do full form. That's let me just do Control Shift N. Okay, let me do this. Okay, string expression. Okay, then D, we want to capture a number string. Okay, we want the first pattern is a number string. That means any, like 3.5, that's a number string. Okay, then followed by another capture. We capture it by the name color. Okay, and this color would be all three parts, either red string or green string or blue string. Okay, so that is the pattern for this, for the pairs of numbers. I mean a number and a color. Okay, and we capture them. So the number will become D, the color string will become C. And what's with this tilde thing? Now those tilde is just the short syntax for the string expression. You know, because when you use this form, it's easier, kind of easier to read, but it's longer. So you have the short syntax. How do I explain the short syntax? Okay, so the short syntax is like this. So string expression, you have A, B, C, you know, A, B, C, D, E, F, G can be many arguments, right? Now the short syntax for that is just A tilde tilde B tilde tilde C, okay? These two are equivalent. Now let me show you why it is. So let's say equal parentheses paste true. You see, so this is just the short syntax for the string expression. So I'm using this one, but the full syntax is just that. Okay, so that's this part. That's the part. That's this part. So we captured basically the number and color. Okay, now we use the replacement feature like we showed before. This replacement feature, we replace it by two expression that turns a number into that turns a string into a number. So D, you see, this D is a number, right? So we turn that into an actual number, a string to number. Now, if that number is greater than X max at C, so X max is here. So what is C? C is one of these color string. So when you say, okay, so let me do it here. So when you say X max, so let me show you what that is, okay? So in Wolfram language, another shortcut is this. When you have F at F bracket X, that can actually be written as F at X, okay? That's always true. Now the F and the X can be any arbitrary complex expression, can be like 1,000 lines of code, okay? So this is kind of the syntactical shortcut. Any of the F and X can be any, you know, expression. So what we have here, max at C, so this X max at C, that is actually just X max bracket C, equivalent, okay? So, but what is the X max bracket C? That is this dictionary. So basically, and C is a color, right? So basically it gives me, if it's green, you know, the result is 13. So what we are having here is that two expression. If this number is greater than max, I mean, if it's greater than one of these numbers, is it true or not? If it is true, then return true. Otherwise, return false, okay? So after these string cases, what we got is a bunch of true and false. Let me show you. Okay, so we haven't defined X max, that's why. So copy X max. So let's put X max here. Okay, run it. So you see, each line becomes just true and false, true and false, okay? Now your job is just merge all these true and false. If there's one of them is true, if there's one single true, that means that line contains a number that's greater than the given, okay? So whenever there's a line that contains true, eliminate this line, okay? So how do you do that? You can just say or. So let me go again. Let's do an example. So paste, okay? So, you know, so or, so we can do or, okay, you use that because there is no true, so that's why the result is false. Now, what is that at? Well, that at is apply, okay? That's a short syntax for apply. So another short syntax is whenever you have F list, okay, that can be written as f at list. Okay, let's replace list by x. It's symbolic, so it can be anything. Okay, that's another short syntax, universal. It doesn't matter in what statement or universal. Okay, so now what you want to do is you want to apply this OR to each of the list of booleans. Okay, and the way you do that is you can just say OR at. this is getting complex. So let me just show you. Okay, so you do that, so you got that. Each one of these true and false means if any of these lists contains a true, it should return true. Okay, so the first one is false, the second one is false, the third one is true because this line actually contains one true. Okay, so that means the game number 3 should be removed because game number 3 contains one of the color 20 red. That is impossible. Okay, because there are a maximum of 12 red. Okay, so now you just got so this true means remove that line. So but how do we know which line that is? Well, this is index number 3. So this is first item, second item, third item. So we want to map a function to this index, but we also get the index. Okay, so let me show you how to do that. Map index. Let me just show you an example. Okay, so let's say ABC. Okay, so basically it applies f to a list, but it gives a function 2 arguments. The first argument is whatever in the list. The second argument is the index of that list. Okay, so map index is one of the map function that can map but also give you the index information, right? So that is that. So that is why you see this map indexed. And what is this function if? Okay, so this function just means, now this line is a shortcut for, let me write the full form of this, the easier to understand way of what this is. Okay, so the easier way to write this, I mean the intuitive way to write this is this way: if x then 0, otherwise y. Okay, that's a function. This function takes 2 things, x and y. Now, so if x is true, return 0. If x is false, return y. So we apply map index to the list and use this function. So this function is our function here. So you see this function. So that means we apply to this list when it is true. For example, this line, game 3, it's true, and just return 0. Okay, so this element becomes 0. Otherwise, give it the second element, so the index of this array. So what you get is, so for example, let's run it with this input. Okay, yeah, you need to map. Okay, so okay. So you need to map. Okay, so let's write it. Map. Okay, map takes 2 arguments. The first one is a function. The second one is a list. Okay, Oh well. Oh, wait, not map indexed, right? Yeah, so let's try it. So there it is. So you see, then you sum them up. That you sum them up because this one means game one, this two means game two, and game three, game four is 0, game 5 is 5. So you add them together is 8. The toy input for day 2 part 1 solution is 8, I believe. So we can check. God, so many wordy. Am I doing good? Am I like... so let's see. Day 2, problem number 1. It says, okay, problem number 1, the toy input solution is 8, correct? Okay, so that is how this line seems so short. You see, this line is equivalent to this line. Okay, I hope I explained it. You know, when I thought about doing this live stream to explain this code, I thought, 10 minutes. But how long have I been? 43 minutes. Oh God. And then we need to explain the code for part 2. That will take 10 or 20 minutes. Then we don't have time to do day 3. So what shall we do? Continue to explain day 2 or start to do day 3? I think I should continue to explain the day 2. Then do another video for day 3 so that each video is more focused on a topic. That's kind of sad because I'm itchy to demonstrate the Wolfram power on the day 3. The day 3 is a bit more complicated because I don't know if you guys have read it. You know, it involves checking adjacent lines. But day 3 can be solved in one single line, just like this, no more than this number of characters. Okay, day 3 part 1. Okay, let's see what you guys are saying. If you are watching, say something, okay? Valley, hello Lunita Zili. Very interesting. I never had to work with regular expression in academics, so this is useful knowledge, okay? Regular expression is vastly useful. You know, if you work in a job, you almost have to use it every day, especially if unless your job is very specialized. You know, maybe doing computer GPU or computer graphics. But in general, if you do web, especially web programming, web dev, you have to use regular expression every day. Okay, so it's great to master. So let's see. Let's read the next. Wolfram solutions are very different from other languages where almost everything are for loops inside for loops. Yes, exactly. Explanations in notebook interface much clearer. Fantastic. Something fantastic, guys. Okay, let's go on explain the day 2 part 2. Okay, the question, the day 2 problem 2 question. Okay, same input, but now for each line, sum the max of each color. Then take their product. Then sum result for all lines. For example, this line: 3 blue, 4 red, 1 red, 2 green, 6 blue, 2 green. Okay, the max of each color is 6 blue, 4 red, 2 green. Okay, 6 blue because there's 3 blue and there is 6 blue. Oh, wait. Sum the max of each color. Okay, so among the draws, the max is, you know, you got 3 blue and 6 blue. 6 blue is bigger, so you got 6 blue. Then among the red, you have 4 red and 1 red. So the bigger one is 4 red, check. Then for the green, the bigger is 2 green. Now 6 blue, 4 red, 2 green, you time them together. So the product is 4 times 2 is 8, 6 times 8 is 48. Okay, so for this line, the answer is 48. And for each line you have to add them. You add all of them together. Okay, so for the sample input, the product for each lines are 48, 12, 1560, 630, and 36, and their sum is 2286. Okay, and this is done by this single line. Okay, so let's just run it. Okay, right. 8. What? Oh, that's the wait. What? Oh, that's the first. That's the first solution. The second solution here. Okay. Paste it. Right. 2286. Check. Now, how does it work? It's almost the same. Okay. So we take the string cases just like before. String cases take 2 arguments. So the first argument, we split the string of the input, so we got a list of lines, list of strings. The second argument to the string cases is a pattern, and with a replacement rule. Okay, so the pattern is the same like before. We grab the pairs of a number and a color. Okay, and we name them D and C. D is a number, C is a color. Okay, once we got this pair, this D and C, we replacement rule, we change them to C becomes to expression D. So that means we change them to the expression. Let me show you what that is. Okay, so that is just okay, so to expression, here is, for example, let's say 8. Okay, so this is a rule. So we want to change it to the color name. C is a color name, and kind of a rule. That means change it to the associated number. Okay, so what you get is, let me show you what you get. Okay, you get the list like that. Okay, this is the first line. It's a list. So blue is a string. Blue becomes 3. Red becomes 4. So basically, it just transforms this. It just transforms this text into this structured syntax. You see, blue 3, check. 4 red, check. Red 1, check. 2 green, check. You see? Okay, so once you have this structured pattern, then what you do is, okay, so then you just sort them. Okay, let me show you. Okay, let's sort the result. Okay, you see, before we had blue 3, red 4, red 1. Now we sorted it. It not sort the items, but also sorts the inner items. Wait, did it? Oh yeah, you need to map to. So we need to map to, actually. We need to map. Okay, so what does that mean? So whenever you see f/@x, that is exactly the same as map fx. Okay, in Wolfram language. Okay, symbolic. So Wolfram language is a lot of the syntactical transformation. Okay, so instead of writing this, cumbersome, you have to type map bracket, like Lisp, paren, nesting. You just do /@ okay? So we are doing sort/add. That means map sort to this list, okay? Let's do it. Okay, now, so you see before, so before it's blue 3, red 4, red 1, green 2. Now it's blue 3, blue 6, you see, because blue got sorted together. Then green, because B before G. Then red is last, because R is, after G, right? So now we got them sorted. Now all we have to do is to convert each one of these lists into a, what Python calls a dictionary, or Ruby calls hash table, or Java calls map. Okay, so remember, when you have a hash table, the easiest jargon is dictionary. Okay, when you have a dictionary, the latter keys overrides the first. So now, why do we sort them? Because when we sort them, you see, it's, the bigger number comes after. So if we turn this into a hash table, then you got blue 6, because blue 3 is overridden. And green doesn't change because 2. And red you got red 6, red 4. Okay, so let's copy that. Let me show you how do you turn this thing into a hash table. Okay, hash table in Wolfram language is called association. Okay, so given that line, you evaluate it, so you got that hash table. Okay, so each line is now just becomes a hash table. So each line becomes a hash table, and then what you do, you see, you sort, you turn it into a hash table, then you just multiply each one of them together. So let me show you. Okay, so for example, we got, so we got this, okay. Now we turn this into association, turn them into a hash table, map. Okay, fantastic, beautiful. Now we sum. So for each one of these association, we want to ignore the key. We just want to not sum, product. Okay, product the numbers. So we can do apply times at this input, then we want to apply it at level 1, I think. Let's see. Yeah, okay. Let me just show you. So you got a product for each line. So what does this level 1 means? Well, in short, any expression is a tree. So level 1, this braces 1 just means apply it to the depth 1. So in Unix jargon, when you traverse a directory, you have depth first directory, subdirectory is depth 2, and so on. Similarly, in any nested syntax, they form a tree. Then you can talk about depth or level. So the word used in Wolfram language is level 1. Okay. So anyway, so that you get just a bunch of these numbers. Then once you have that, you just total. Okay. So the solution for the toy input is 2286. Is that correct? Yes, it is. Okay. So I hope that explained it. Does that make sense, you guys? How many people are watching? 3, 7, okay, 9. Good, not too bad. Okay, does that make sense? Okay, now we talked for 56 minutes. Shall we? I think that's it. Or I can try to start to do day 3, but I don't think it's good, because I think it's simple, but if I actually do it, it's gonna be at least 30 minutes if I focus on it. But usually I'm gonna talk about it, then it's 40 minutes, then it's not done. Okay, no. Okay, thank you guys. Thank you for watching. Hope you like it. Pay me if you like it. Okay, go to my website, solly.info. You see my PayPal and Patreon. Okay, last 5 minutes, question and answers. Any questions? Do you think are you impressed by the power of Wolfram language? Okay, one single lines of code, less than 200 characters. Okay, let's count the characters. Let's how many? 170 characters. Okay, that's for the part 2. Wait, is this where are we? So what is this? Yeah, so this is today's talk show. I just demoed some of the code, but we can go to, okay, color it. So let's see. Yeah, okay, let me just talk random for a while. Talk random about things, okay? So talk random. So let me show you some other neat features of Wolfram language. Okay, so let's see. Yeah, so in the past few days, instead of working on advent of code, I worked a lot on my Wolfram language tutorial. In particular, okay, hold on a second. Let's see. I wonder, like, what can you see here? Yeah, so I worked a lot on the Wolfram language, in particular on the association data structure. So if you just search for Solly Wolfram language tutorial, so I have a whole tutorial. So there is an association data structure section. Association is Python's dictionary or hash table. Okay, and tremendous. So I worked on it for a few days. Then I worked on regular expression. So because the advent of code requires a lot of regular expression. And what's fascinating of Wolfram language that stand out is that you got this string expression, which is an alternative pattern, string pattern for analogous to regular expression. We just showed a lot of that power today. You see. So can you do this in regular expression? Yes, you can. Should we try? Actually, so we can represent this. You can see this string expression syntax. We can represent that in regular expression, which is not hard at all. So in fact, for example, this line in regular expression would be REGE regular expression. Okay, so in regular expression, first of all, you want the number string. So a number string is dash backslash D, that stands for digit, one or more. Now in Wolfram language, you need 2 backslash, just like Lisp, because in Wolfram language, the string pattern for regular expression is not special string. There's no special regular expression string. You just have one single string data type. And in string data type, the backslash is escape. So when you want to have backslash D, which stand for digits, you need backslash D. Okay. So anyway, so now we have a digit followed by space, then a color. A color is a parenthesis, red, alt, green, alt, blue. Okay. Now we need to capture these. So in order to capture, we need paren. So paren, and actually that will work. But now, so this this line is actually kind of similar to that, okay? But the issue is that now the capture pattern is represented by, in Wolfram language, $1, $2, okay? That represent this captured pattern, okay? That's about regular expression and string expression. Do you know why? So you see, when doing the advent of code, my goal is basically to show off Wolfram language, right? When you have a programming problem, there's a lot of things you have to think about. Efficiency of code, readability of code, maintainability of the code. You don't want cryptic, you don't want, cryptic thing. Unless you are playing programming golf, when you are doing programming competition, like Perl golf, then the crypticality is what you need. That's the first prize. Similarly, for advent of code, you see, advent of code is kind of, the internet, fun programming, but there is no measure of efficiency of your code. There's no measure of your quality, of your generality of your code. They don't care. All they care is like, show me the answer, right? Like I talked before about the advent of code, which is, that's the purpose, right? It doesn't need to say how efficient. Suppose this number of lines is a billion. I'll bet most of this advent of code, 95% of the advent of code solution will break because they'll run for days. So you have to care about efficiency. And then you also have to care, So anyway, when in general, when you solve a problem, there's a lot of concerns. But for the advent of code, for me, I choose the most dramatic solution. The shortest seems to be the best approach because that's what people see, right? Yes, Wolfram language can also understand natural languages, but I haven't I haven't really explored that. There's a lot AI building, machine learning building. Like one single line equals to 10,000 lines of Python libraries. One single function name, Right. I have to show that another day. Joman says, does that pink window counts the keystrokes? The pink window you see here, that is all my, how do I, okay, so let's try to move that here. It counts the, all every command I do, okay? For example, I move down, I move up or down by paragraph, or I go to the top of the buffer. Can you see it? Actually, no. Yeah, okay, so let's... Okay, so if I go to the bottom of the buffer, you can see end of buffer, right? Now, if I go to the top, you'll see beginning of a buffer. Now, if I just press this key, which calls start end of line or block, because that's what the command do. Either move to the end of line, for example, I do it, or if it's already in the end of line, you'll just move to the next paragraph or block of code, or I can move up. So every keystroke and their corresponding command are logged in Emacs, because that's how Emacs works. Emacs doesn't, in essence, the gist of Emacs is that all it cares is your keystroke, because every keystroke eventually corresponds to one command, and that command will do whatever, including inserting characters. For example, new buffer, you see I just called new buffer. I press U because I'm using soft-like keys, so that means command mod activate. Okay, or actually that means, you see, U is insert mod activate. Okay, so U, then I can type ABC. So you see, when you type ABC, that actually calls insert command, insert character. Okay, it's not shown here. You see, it's not shown here because I filtered it out. Because otherwise, when you type something, then this pink window will just insert 10,000 times, So that's why the pink window doesn't show that. But basically, it records all your commands. If you want to see the code for the pink window that removes, filter that I can show you, not here, okay? I can show you. Let's go to my init. Okay, Kasa init. I want to go to, okay, command log mod, go to packages. Okay, so let's adjust the window. Log, wait. Okay, it's not here. It's in my other, yeah, okay, there it is. Command log mod is written by someone else. So I modified a little bit. Command log mod.el. So you can see the filter. Where is my, there it is. So you see, command log, command exceptions. So I added mouse drag region, mouse set point, because otherwise every time you click, it'll say click, code, or every time you, so, there it is. You see self insert command. So if I comment this out, run this part of code, and now I open a new buffer, switch to insert mode, start typing, and typing some more, and now you can see, you see, they start typing and typing some more. It went there, and they are actually calling this self insert command. You see, 33 times. Why 33? Because there are 33 characters. You see, okay. Okay, that's it. Yeah, I wanted to show you one more thing about Wolfram language. So I've been, it's fun thing. Okay, so that's yeah, transliteration. You can actually transliterate Chinese. So, okay, close that. Go back to Wolfram language. Go down. Paste it. So you can see. Transliterate, these are Chinese characters, and I can type some more Chinese. Let's see, Windows Chinese input. Let's say 今天 means today. Okay, now let's switch back to US keyboard and enter. Okay, now remember this last part is pronounced 今天. I just typed. Okay, now shift enter. You see, 今天. You see, it can transliterate Chinese. Fantastic. And you can type Japanese, Japanese too. And actually, I found out that ChatGPT can also do it because I just tried it here. Okay, that's it. That's it for today. Thank you guys. Bye. Pay me, okay? Donate me. Thank you. I read in Stephen Wolfram's blog, he uses a keylogger. Yes. Commercial, not Wolfram language, to record keystroke. Yes, he recorded lots of things in one of his blog about 4 years ago. Bye, guys. Can you try speak with that input? That's very interesting. Let's try that. Say something English. Okay, let's try English first.
Say something English.
Okay, let me adjust the audio.
Say something English.
Okay, now let's try this Chinese. 试试看中文今天。No, it doesn't. Yeah, interesting. So wait, so does it? So let's see. Let's look up options. Can you actually? Maybe not, because then you require. Produces sound using your computer's operating system. Spoken string gives text for speech generated by speak. Gives text. Oh wow, wow, well, that's a very interesting thing. So you say spoken string. So let's see how it transliterate the English. It doesn't. That's not. But anyway, is there an option for Chinese? I don't think so. Okay, bye guys.